So you may have noticed that when we talk about ions, we tend to talk about some of the elements that always seem to have the same charge. So we already know that things can gain or lose electrons, and that's how they become charged. So if something becomes a negative charge, that's called an anion. And we know that that is when it gains an electron. And if something has a positive charge, that's called a cation. And things become positively charged by losing electrons. Now, there's a rule that goes with gaining and losing electrons. Elements just don't gain and lose however many electrons they feel like it. They like to have something that follows the Octet Rule. And that means elements like to have 8 valence electrons. So that means in the highest occupied energy level, an element will gain or lose electrons so that it gets 8. And whether it gains or loses depends on what is easiest. So what is most likely to happen due to the amount of positive in the nucleus and how many electrons it already has. Is it going to be easier to lose 1 or 2 electrons to get to 8, or is it going to be easier to gain 1 or 2 electrons to get to 8? So let's look at some electron configurations to help us figure out whether or not they're going to gain or lose electrons. So let's start with sodium. If we were to write a quick electron configuration for sodium, so sodium has 11 electrons, so its full configuration would be 1s2, 2s2, 2p6, 3s1. Okay, so how many electrons, valence electrons, does sodium have right now? Well, its highest energy level is the 3rd energy level, and so it has 1 valence electron. Now it really wants 8. So it currently has 1 valence electron, it really wants 8. With only 11 protons, does it seem more likely that sodium is going to cram 7 more electrons into that 3rd energy level, or is it just going to lose the 1 and then have the 8 in the 2nd energy level? Well, it's going to be easier for sodium just to lose the 1 electron. So sodium is going to become a +1 charge, and it would have an electron configuration of 1s2, 2s2, 2p6. So now its highest energy level is the 2nd energy level, and it has a total of 8 valence electrons, so now it follows the Octet Rule. Let's look at boron as our next example. So boron has 5 electrons. Its electron configuration would be 1s2, 2s2, 2p1. Okay, so how many valence electrons does boron have right now? Well, its highest energy level is the 2nd energy level, so it has 3 valence electrons total. If we're trying to get to 8, we're either going to gain 5 or, let's not use a plus sign, let's say add 5 or lose 3. Well, for boron, it's going to be easier for it to lose the 3 electrons than for it to gain the 5. So boron is going to become a +3 charge because it's going to lose 3 electrons. Its new configuration would be 1s2. So now, and that's kind of a weird one. So it's going to lose its outer 3 electrons, and it's actually more stable having only 2 than 8. So it kind of follows the Octet Rule, kind of not. Let's look at fluorine as our last example. So fluorine's here with 9. So it would have an electron configuration of 1s2, 2s2, 2p5. Now fluorine has its highest energy level is the 2nd energy level. It currently has 7 valence electrons. So we could either add 1 or lose 7. Which do you think is more likely? Well, it's more likely that fluorine is going to add 1 electron. So it's going to become a -1 charge. And its new electron configuration would be 1s2, 2s2, 2p6. So now its highest energy level is the 2nd, and it has a total of 8 valence electrons. So if you notice, the goal is always to get to an electron configuration that looks like a noble gas. So sodium, if it loses an electron, it would look like neon. Boron, even though it only ends up with 2 valence electrons, it's going to look like helium. And then for fluorine, if it gains an electron, it will look like neon. So the goal of the octet rule is for elements to gain or lose electrons so that they end up looking like a noble gas, so that they have a total of 8 valence electrons. And that's how we get to our common charges for some of our metals and our nonmetals.